Hi, so we start with the next capsule, 8a. We continue with the study of determinants. Now let us look at some applications. We have already seen that if A is a square matrix of size n cross n, the following are equivalent. Rank of A is n, equivalently, nullity of A is 0, and determinant of A is not 0. These are equivalent statements. Of course, this in turn means that A is invertible. Now let us look at a system of linear equations. Ax equal to b. The rank of A is already n. A is an n cross n matrix. If I augment it, I'm going to get an n cross n plus 1 matrix, but the rank anyway is n only. So even the augmented matrix will have rank n. So the system will have a solution, and this solution will be unique because A is invertible. Nullity is 0. On the other hand, if rank is less than n, that means the nullity is positive and the system has a solution, then it will have infinitely many solutions. We are interested in the case when b is 0. We are interested in the case when b is 0 because where we know that 0 is always a solution. So in the case when b is 0, we know that ax equal to 0 certainly has a solution called the trivial solution or the 0 solution. Now, when will it have the only the trivial solution, the unique solution, and that solution will be 0? That will happen if the determinant is not 0. The rank is n, or the determinant is not 0. If the determinant is 0, then besides the trivial solution, it will have a non-zero solution also. So this is something that you should keep in mind in what follows. Now we are going to use this simple observation to prove the theorem that if you take k vectors v1, v2, vk in Rn, then these vectors are linearly independent if and only if the Gramian is non-zero. What is the Gramian of a system of k vectors? You simply take Vj transpose Vi. Vj transpose is a row vector. Vi is a column vector. So Vj transpose Vi is a real number. And this matrix is a symmetric matrix. And its determinant is called the Gramian. And so if the vectors are linearly independent, the Gramian is going to be non-zero. Conversely, if the Gramian is non-zero, the vectors are going to be linearly independent. It turns out that the Gramian is always going to be non-negative, but that's a different story altogether. We are not going to get time to prove that. So let us get to the proof of this. Suppose that the vectors v1, v2, vk are linearly dependent. That means there are scalars c1, c2, ck, not all 0, such that c1, v1 plus ... plus ck, vk is 0. Multiply by Vj transpose on the left, and then we get C1 times Vj transpose V1 plus ... plus Ck times Vj transpose Vk is 0. So let J run from 1 to K. What do I get? I get a system of K linear equations in K unknowns, namely C1, C2, Ck. And the right hand side is 0. We know that 0 is always a solution, but here we have another solution. There are scalars C1, C2, Ck, not all 0. Focus on the phrase not all 0. So this system star admits a non-trivial solution. So the determinant of the system must be 0. What is the determinant of the system? The determinant of the system is exactly the Gramian. So the vectors are linearly dependent. The Gramian must be 0. Now we have to prove the converse. Now let us go to the converse. Assume that the vectors v1, v2, vk are linearly independent. If the vectors are linearly independent, we have to show that the Gramian is non-zero. It's proof by contradiction. Suppose the Gramian is 0. Then we are going to arrive at a contradiction. Okay. Now the Gramian is 0. The Gramian is a square matrix. So if the Gramian is 0, then I form the system of equations with this square matrix, and this system of equations will have a non-trivial solution. That means we can find C1, C2, Ck not all 0, such that C1 times Vj transpose V1 plus dot 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 plus Ck times Vj transpose Vk is 0, J running from 1 to K. By renaming the vectors, we may assume that Ck is not 0. Well, if you rename the vectors, then the equations or the ordering of the equations will also get rearranged, but that doesn't matter. I'd like you to convince yourself that I can rename the vectors V1, V2, Vk, and I might as well assume that C1 is non-zero. Once I assume that Ck is non-zero, once I assume that Ck is non-zero, I can divide by Ck, and I might as well assume that Ck is 1. So here we are in a situation, and I'll take out the Vj transpose common. So it's Vj transpose multiplied with C1 V1 plus C2 V2 plus dot 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 plus Ck minus 1 Vk minus 1 plus Ck Vk, but Ck is 1, so Vk is 0. And J runs from 1 to K. Let us write this. Let us call this vector C1 V1 plus C2 V2 plus dot 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 plus Ck minus 1 Vk minus plus Vk. Let us call it nu. Suppose we show nu is 0. Suppose we arrive at the fact that the vector nu is 0, then what will it imply? It will mean that the linear combination C1 V1 plus C2 V2 plus dot 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 plus Ck minus 1 Vk minus 1 plus Vk is 0, and the coefficient of Vk is 1 and 1 is not 0, and that will contradict the fact that V1, V2, Vk are linearly independent. We are assumed that V1, V2, Vk are linearly independent, remember? And so how can that be possible? How can C1 V1 plus C2 V2 plus Ck minus 1 Vk minus 1 plus Vk be 0? That will not be correct. So that we would have arrived at the contradiction. Correct? So our job is to show that this vector nu is 0, and that will finish the proof. All right. So let us write these things. Vj transpose nu equal to 0 as a system. Nu is a column vector, and then this V1 transpose V2 transpose dot 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 Vk transpose. This matrix now becomes a K cross N matrix, or a K cross N system of equations. Now what happens is that also let us look at this C1 V1 plus dot 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 Ck minus 1 Vk minus 1 plus Vk equal to nu. Let us take the transpose of this. We get C1 transpose V1 transpose plus C2 transpose V2 transpose plus dot 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 plus Ck minus 1 Vk minus 1 transpose plus Vk transpose equal to nu transpose. We observe this thing written in green, and let us do the following. Suppose in this system, I can perform elementary row operations, correct? So what elementary row operations I'll perform? I'll add to the last row C1 times the first row. I'll add to the last row C2 times the second row. I'll add to the last row Ck minus 1 times the K minus first row. Then what happens to the last row? The last row becomes Vk transpose plus C1 V1 transpose plus C2 V2 transpose plus dot 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 Ck minus 1 Vk minus 1 transpose. In other words, the last row has become nu transpose. Okay, the last row has become a nu transpose. There is a typo here. It should be plus Rk prime equal to Rk plus C1 R1, Rk prime equal to Rk plus Ck minus 1 Rk minus 1. I'll make the change when I share the slides with you. So you understand what I'm trying to say. I already spoken the thing correctly. So what do we get? We have obtained a new system, V1 transpose dot 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 Vk minus 1 transpose. The last thing is nu transpose nu. So now let us do the last row. Let us multiply the last row. Let us compare the last entries in this equation. Comparing the last entries in this equation, you see that nu transpose nu equal to 0. If nu transpose nu is 0, then nu must be 0. How? Please think about it. Write nu as a column, alpha 1, alpha 2, dot 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 alpha n. Nu transpose is a row, alpha 1, alpha 2, alpha n rho. So nu transpose nu is 0 means alpha 1 squared plus alpha 2 squared plus dot 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 plus alpha n squared is 0. The alphas are real numbers. So each of the alphas must be 0. So nu is 0, and that's exactly what we wanted to prove. And so we have proved completely the theorem that when you have a system of when you have a k vectors in Rn, the k vectors in Rn are linearly independent if and only if the Gramian is non-zero. The Gramian, as I said before, can be interpreted as the volume of the k parallelepiped in Rn. But before I prove that, I'll have to give you an interpretation, or I'll have to give you a precise definition. What is the k-dimensional volume in Rn? And that will have to be done carefully, and you have to develop that theory very carefully. So I can't really get into that. I can give you a reference later if you like. If you maybe you can send an email. I'll give you the reference if you're interested. Now let us take the next thing, the adjugate matrix and Kramer's rule. The word adjugate matrix is used to denote the matrix obtained from A. A is a square matrix. A is a square matrix, and using the square matrix, I'm going to do something. I'm going to replace the ijth entry, Aij, by its cofactor, capital Aij. Cofactor, not minor. Please remember, cofactor comes with a sign, -1 to the power I plus j. So replace each entry by its cofactor, and then take the transpose. Don't forget to take the transpose. It's very important. So the adjugate of A is a matrix of cofactor with a transpose. Some books call this right-hand side of star as the adjoint, but we are going to studiously avoid this phrase adjoint because it can be potentially confusing. The adjoint of a matrix is used very frequently to denote the conjugate transpose of a matrix. If you take a matrix A whose entries are complex numbers, and you take A bar, you replace each entry by its complex conjugate and take the transpose, that object is called the adjoint of A. And so clearly it can cause confusion. So I'm not going to use the word adjoint. I'm going to use the word adjugate. Classical books call it the adjugate, and I'm also going to call it adjugate. Now, let us look at the expansion of the determinant by rows. What is the expansion of determinant by rows? Summation j from 1 to n, summation j from 1 to n, aij, capital Aij equals determinant of A. Equation 1, that is summation by rows. Now let us tamper the matrix. Let us knock off let us take a I prime, let us take another row index I prime, knock off the I prime row and replace it by the ith row. So we get a new matrix A naught. So in this new matrix A naught, the row Ri and the row Ri prime are one and the same. So A naught has two identical rows. A naught has two identical rows. So we know that the determinant of A naught must be 0. A naught has two identical rows, and so its rank is strictly less than n. So the determinant must be 0. Now what we do is that we do the Laplace's expansion. We do the expansion of this determinant using the I prime through. So the entries of A naught are A I prime j 0 superscript 0, and the corresponding cofactors are capital A I prime j superscript 0. So we get this expansion using the I prime throw. But what exactly is happening? The I prime throw and the I throw are identical, isn't it so? So I prime j 0 is exactly the same as Aij. So this expansion simply becomes summation Aij A naught I prime j. But now let us look at this A naught I prime j. Now A naught I prime j must be the same as A of I prime j. Now why is this so? I'd like to stare at this. When you're computing the cofactor of the I prime when you're computing the cofactor of A naught superscript 0 I prime j, you're going to remove the I prime row, right? The tampered row has been removed. Correct? The tampered row has been removed. That is why when you're computing the cofactor, A naught I prime j is going to be identical with A I prime j. Because A naught is obtained by A by tampering the I prime row, but the I prime row has been removed while computing the cofactor. So it is going to be so the cofactor so you're going to get the same cofactor of A. So now let us substitute this in the last equation. What does the last equation read now? Summation j from 1 to n aij ai prime j equal to 0. That is equation number 2. So you got this equation number 1 and equation number 2. Aij, capital Aij, the same j on both sides. So the same I on both sides. Aij, capital Aij, determinant of A. Here I'm having Aij, but capital A I prime j. I'm getting 0. So let us stare at these two equations, 1 and 2. Let us put them together. So let us combine them. Summation Aij capital A I prime j. If I and I prime are different, I'm going to use 0. If I and I prime are equal, it's going to be determinant of A. The two equations can be written together, right? And how many equations are there? This I is free and I prime is free to vary from 1 to n. So there are n squared equations. But what does this n squared equation tell you? This n squared equation tells you that the matrix product, this n squared equation basically tells you that the matrix product of A times adjugate of A is determinant of A times identity. So here is where you need the adjugate is a transpose of the matrix of cofactors. A I prime j has to become the j I prime term of the transpose. It is to interpret the left hand side as a matrix product that you need the to transpose the matrix to apply the transpose operation while calculating the adjugate. So we get the fact that A times the adjugate of A is determinant of A times identity. In particular, if the determinant is non-zero, I can divide by the determinant and I will get A times adjugate of A upon determinant of A is I. In other words, the inverse of the matrix A is the adjugate of A divided by the determinant of A. This is a formula that you have probably seen in your 12th standard for 3 by 3 matrices. And this formula is sometimes known as the Cramer's rule for finding inverse. Why is it called the Cramer's rule for finding inverse? You may have seen a different Cramer's rule. We will come to that immediately. If we have n equations in n unknowns, and we want to solve Ax equal to b, and I know that the determinant is non-zero. I'm telling you that the determinant is non-zero. And what is the solution? The solution is unique, and the unique solution is x equal to A inverse of b. But I just found out that A inverse, I have found a formula for A inverse, and so I get x equal to adjoint of A upon determinant of A applied to b. Now I want you to do an exercise. Now I want you to take a 3 by 3 matrix A11, A12, A13, A21, A22, A23, A31, A32, A33, X1, X2, X3, B1, B2, B3, and write down this right hand side explicitly. And I want you to convince yourself that this expression that you get is exactly the familiar Cramer's rule that you studied in 12th standard for solving 3 equations and 3 unknowns. Please do this exercise and convince yourself of this. Finally, we will prove 2 theorems that you have been waiting for. The determinant of AB is determinant of A into determinant of B. That's the first theorem, the product theorem for determinants. A and B are 2 n cross n matrices. Determinant of AB is determinant of A into determinant of B. First of all, case 1, determinant of A is 0. So the RHS is 0. Well, determinant of A is 0 means rank cannot be n. The rank cannot be n, the row rank cannot be n. The row rank is not n means the rows are linearly dependent. Rows are linearly dependent means there exist scalars alpha 1, alpha 2, alpha n, not all 0, such that summation alpha j rj is 0. What is the jth row of a matrix? How do I pick out the jth row of a matrix? Multiply on the left by the row vector ej transpose. Rule number 2. There are 4 basic rules for matrix multiplications. So the rj can be written as ej transpose of A. And so I got summation alpha j ej transpose A equal to 0. Now multiply this by B. Multiply this on the right hand side by B. You get alpha j ej transpose AB equal to 0. But ej transpose of AB is the jth row of AB. That means that the rows of AB are linearly dependent. If the rows of AB are linearly dependent, that means the determinant of AB is 0. So right hand side is 0 and the left hand side is 0, and the theorem is proved in this case. Case 2. The determinant of A is non-zero. Determinant of A is non-zero. And determinant of B, let us call it C1, C2, Cn. Think of A as a fixed matrix and think of B as a variable matrix. So I can think of C1, C2, Cn as arguments of a function. What function? No prizes for guessing. F of C1, C2, Cn will be, I'm going to cook up a function. I'm going to cook up a function C1, C2, cook up a function f of C1, C2, Cn, and I'll prove that f is multilinear and skew symmetric. How do I do that? A is fixed. So take, and C1, C2, Cn are the n columns of B. So take AC1, AC2, ACn, they're column vectors, and take the determinant of that. So f of C1, C2, Cn equal to determinant of AC1, comma, dot, 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 comma, ACn. And I'm dividing by the determinant. Why am I dividing by the determinant? You will see in a minute, in a moment, it will become clear. This function is multilinear, because if I replace C1 by alpha C1 prime plus beta C1 double prime, then the first column here will get split into alpha A C1 prime plus beta A C1 double prime, and the determinant will be a sum of 2 determinants, etc. So f is obviously multilinear. It is skew symmetric, because if I switch 2 columns here, the corresponding 2 columns here get switched, and so it picks a minus sign. Normalization, I have to calculate the value of f at E1 cap, E2 cap, En cap. What is that going to be? Determinant of A E1 cap, comma, dot, 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 A En cap. What is A E1 cap? The first column of A. What is A E2 cap? The second column of A. So what is the numerator? Determinant of A. What is the denominator? Determinant of A. So what's the value? 1. The normalization condition is also satisfied. But the uniqueness theorem, f of C1, C2, Cn must be the same as the determinant of C. Remember, C1, C2, Cn are the columns of B. So the left hand side must be the determinant of B, and the right hand side is AC1, AC2, AC1 are the columns of AB. And so when I multiply by, when I clear the fractions, I get determinant of A into determinant of B is determinant of AB, and the proof is complete. This is the product theorem, and as an application of the product theorem, we shall prove that determinant of A equal to determinant of A transpose. Now, is an easy exercise to check that determinant of A will be equal to determinant of A transpose when A is one of the 3 elementary matrices. Remember, we have 3 elementary row operations. Switching 2 rows corresponds to elementary matrix Pij. Adding to a given row a multiple of another row, that corresponds to an elementary matrix Eijc. Third thing is multiplying the kth row by gamma naught 0. That matrix was called MK gamma. For all these 3 cases, you can directly check the determinant of A is determinant of A trans. In fact, 2 of the matrices are symmetric matrices, except the Eijc. And for Eijc, the determinant is 1. Both sides are 1. So you can check this directly for the 3 elementary matrices. Now we will prove it for general. Now, if A is singular, then A transpose is also singular. Because if A is singular, the rank of A is strictly less than n. Rank of A transpose is also strictly less than n. So both the determinants of both sides are 0. So the interesting case is when A is non-singular. When A is non-singular, we know that a non-singular matrix can be written as a product of elementary matrices, E1, E2, E capital N. Each EJ is an elementary matrix. So what is A transpose? En transpose, E1 transpose in the reverse direction. So let us take the determinant of A transpose. Determinant of A transpose is determinant of En transpose, determinant of E1 transpose. I have applied the product theorem. But for the elementary matrices, I had checked the determinant of A equal to determinant of A transpose holds for elementary matrices. So I get determinant of En determinant of E1. But again, I'm going to apply the product theorem, and I'm going to write it as determinant of, well, first, determinant of En is a real number. Determinant of En minus 1 is a real number. So these factors here can be permuted. So these factors in this line, in the middle line, determinant of En minus 1 determinant of E1, these are product of real numbers, and so I can rearrange them in whatever order. I'll reverse the order of these determinants, and then I get determinant, and again apply the product theorem, determinant of E1, E2, En. That E1, E2, En is A, and I get determinant of A. The proof is complete. So this completes all the important theorems. As an application, show that if A is a skew symmetric matrix of odd order, the determinant of A is 0. So with this we shall stop the lecture number 8.